A cone is filled with water. Two solid spheres are placed in the cone as shown in the diagram, and water spills out. The spheres are touching each other. Each sphere touches the cone all of the way around, and the top of the top sphere is level with the top of the cone. The larger sphere has a radius twice that of the smaller sphere. If the volume of the water remaining in the cone is 2016 pi, what is the radius of the smaller sphere? The volume of a sphere with radius r is 4/3 pi r cubed. The volume of a cone with radius r and height h is 1/3 pi r squared h. We must label this diagram, and here we go. I will label it A, B, C, and then we'll call the center O, we'll call this center Q, and the very bottom we'll call P. Now, this from here to here, AC, represents the radius of the cone, so I'll just write RC there. This is the radius of that small sphere. We'll just call it R, obviously. And these guys are the radius of, or the radii, I should say, of the large sphere. And they told me that the large sphere, the radius is twice of the smaller sphere. So I can just write 2R right here and 2R. And these are 90 degrees, just in case you cannot see that. That's 90 and that's 90. Why? Because those are tangent lines. They touch the other line, and if it's tangent, it will create a 90-degree angle. And this is also a radii, so that's also 2R. And I think that's pretty decent labeling for now, so let's move ahead with the question. The first step in this question is to understand that we have a similar triangles relationship. And those similar triangles are triangle OTP being similar to triangle QUP. So OTP, this is T and this is U. So OTP is this triangle right here, and that's similar to QUP, and I hope you can see that. They're pretty much got the exact same angles. So based on that, OT over QU is the same as OP over QP. Well, OT is 2R and QU is R, and that's the same as OP over QP. So that basically means when the R's cancel out, that 2QP is equal to OP. All right, so that is very helpful, and that allows us to get a relationship between the height, which is the top to bottom, that's the height, H, of the cone, to R, and that's pretty much going to be what we need to solve this. All right, well, OP, which is the distance basically from here all the way down to there, is equal to OQ from here to here plus QP from there to there. So OQ plus QP. And OQ from here to here is 3R. It's this guy plus this guy. So that's 3R right there. So put that in here, 3R. And then QP, well, QP I don't know yet. So I'll just leave it there for now. But I know this relationship, that 2QP is equal to OP. So that's very helpful. So instead of this OP, I'll just put in 2QP. So there we go. 2QP is equal to 3R plus QP. And then if you put 1 QP on the other side, we get just QP is equal to 3R. So there we go. That's a very helpful finding, that the distance from Q to P is 3R. So I'll just put that in here, 3R. And then also we know that 2QP is equal to OP. So that means 2 times QP is equal to 6R, and that's equal to OP. So that is OP. So those are two very important findings. Now what's H? The height of the cone. Well, the height of the cone is all the way from C down to P. Okay, let's count now. 2R, 2R, that's 4, 5, plus 3, 8. So the height is 8r. So those are very, very important findings. And now we can proceed with the second part of the question. The second part involves getting the radius of the cone in some sort of a relationship with r, something. So that is what we have to do. Because here we got the height in terms of r. So we have to now get the radius of the cone in terms of r. And once we have those two things, we can solve the question. Well, to do that, we have to use another similar triangles relationship. This time the triangles are ACP and OTP, a triangle that we had already looked at. So let's look at that now. Where is ACP here? ACP, so all of that big guy right there, that's one triangle. And then OTP is this one, OTP. Those are similar triangles because they share the same angles. So that basically means that AC over OT is equal to CP over TP is equal to AP over OP. All right. So let's label in AC is RC, the radius of the cone. OT, do I know anything about? Yeah, it's 2R. Okay, great. CP, that's the height, remember? And the height, I already figured out a relationship, so that's 8R. TP, do I have anything? TP, I don't really have anything yet. Okay, so I'll just leave TP for now. AP, again, I don't think I have anything for AP just quite yet. So I'll just put in AP for now. And then OP, now that one I have from O down to P, that's going to be 2 plus 1 plus 3, and that's 6R. Okay, so that's a pretty good set of findings. However, I'm going to need to know the value of TP in order to really figure this out. And that's not a problem because I can use Pythagoras. I can use Pythagoras on that triangle right there to figure out TP. So TP squared plus TO squared is equal to OP squared. So that means TP squared plus TO, what is that, 2R squared is equal to OP squared. And OP was what, 6R, right? So there we go. So that means TP squared is 36R squared minus 4R squared. So that's 32R squared is TP squared. So TP is going to be root 32. So what's that? 4 root 2? 4 root 2R. Okay, great. So now we can go back and use that relationship. So RC over 2R is equal to 8R over TP, which is 4 root 2R. Okay, so that means RC is equal to 16 over 4 root 2R. And that, of course, that simplifies to 4 over root 2R. All right, great. Exactly what I needed. RC in terms of R. So now that we have this relationship and we have this relationship, we can now solve the question. So here we go. If you were to interpret the question correctly, you would write the following: that the volume of the first sphere and adding to that the volume of the second sphere plus the volume of water, which they had said is 216 pi, equals the volume of the cone, right? Because you have the volume of the first big sphere, the volume of the second sphere, and all the water that's been, filling the other parts. That all combined equals the volume of the cone. So that is how we're going to proceed with this question. Now, they are very helpful by giving us some formulas. The first volume is 4/3 pi r cubed plus 4/3 pi small r cubed, and then just 2016 pi, and then the volume of a cone is 1/3 pi radius of the cone squared times the height. Okay, the first thing we can do is eliminate all the pi's, so all these pi's can go. And then we can multiply through by 3. Multiply through by 3, and that will get rid of the fractions. So when you do all that, you will get 4r cubed plus 4 small r cubed plus 6048. Remember, I'm multiplying through by 3. And this gives me just rc squared h. Okay, great. Now all I have to do is substitute everything in. So when I do that, this big R, remember, was twice small r. And then this is just 4r cubed. This is 6048. Now RC, in a very helpful way, I got it in terms of small r. So that's going to be 4 over root 2 r all squared. And then h, again, I got in terms of small r. So that's going to be 8r. All right, I only have one variable. I can solve this. So 2 to the power of 3 is 8. 8 times 4 is 32. So that's 32r cubed plus 4r cubed plus 6048. This is going to be, let's see here, 4 times 4 is 16 over root 2 squared is 2. So 16 over 2 is going to be 8. So 8r squared. And then times 8r. Okay, so this is 36r cubed plus 6048. And this is 64r cubed. Bring the 36 over. 64 minus 36 is 28r cubed over, and that's equal to 6048. 6048 divided by 28 is 216. And then if you take the cube root, you get r is equal to 6. And there you go. That's the radius of the small circle. And that is what they wanted us to figure out. What is the radius of the smaller sphere, I should say, not circle. So number 24, the answer is B. A container in the shape of a triangular prism stands on one of its triangular faces. 3 spheres of radius 1 are placed inside the container, each touching the triangular bottom. Each sphere touches 2 of the rectangular faces of the container, and each sphere touches the other 2 spheres. A 4th sphere of radius 1 is placed on top of the 3 spheres, touching each of the 3 spheres on the top of the prism. The volume of the prism is closest to. This question is going to be done in a few steps. Step number 1 is the volume formula. And that volume formula is just going to be the area of the base, which is a triangle, 1/2 base times height, times the height of the entire prism, and I'll just call that large H. So there we go. That is the volume. So individually, I obviously have to figure out the value of B, H, and large H. So the first thing I want to do is draw the base, which is an equilateral triangle. That's the only way it could be. And let's see what happens when I put in 3 spheres. Now, the challenge here, of course, is that we are dealing with a question that talks in 3D, but my diagrams will be in 2D, but eventually I'll give you a 3D diagram. But for step number 2, a 2D diagram will be sufficient. So let's draw in those 3 circles that will represent our spheres. So here is the base, and each of these red circles represents a sphere. So what I'm going to do, the first thing, is draw the radii. And those radii will help us sort of get an understanding of what is the sizes of the lengths. So here's the first one, that's tangent, right? And then from the center of the circle, we draw another one. Let's connect these. And that should be good enough to figure out the lengths of this triangle. Because remember, that's going to be this part right here. I have to figure out the base and the height. Okay, So each of these spheres has a radius of 1. So this is 1 right here, the distance from there to there. And this is 1 from here to here. Similarly, this is 1, and this is 1. So this is 1, this is 1, this is 1, this is 1. Okay, now concentrate on this triangle right here. That is a 30, 60, 90 triangle. How do I know? Well, one thing is for sure, the way I drew this is a tangent, so that's a right angle. And then because it's an equilateral triangle, that angle there would be 60. So if you chop it in half, this little guy in here will be 30 degrees. And therefore this angle right there, this angle from here to here, that would be 60. And you guys, if you're in grade 10 and you're at this point of the math contest and you're practicing these kinds of questions, this should be pretty self-explanatory. So that 30, 60, 90 triangle, I'll just draw a rough sketch of it like that. This is 30, 60, 90. And then we know that this side is equal to 1. So I want, what is this side? Because that's going to help me figure out the length of that side. Well, according to 30, 60, 90 triangles, the ratio of the sides, x over 1, will be the same as root 3 over 1. So x is just root 3. So there we go. So this distance from there to there is root 3. And then because of the symmetry of the diagram, that will also be root 3 over there. So this entire base looks to me like it's root 3 plus 1 plus 1 plus root 3, which would be 2 plus 2 root 3. Okay, so might as well plug that in there. Why not? 2 plus 2 root 3. Okay, so next I'll concentrate on h, and then at the end we will figure out our value of the big H. Okay, well h, small h at least, is right there. I can figure that out pretty easily. Again, using a 30, 60, 90 triangle. So that 30, 60, 90 triangle this time is this guy. So let's just draw a very brief sketch of that. This is my h, and this is 90 degrees. This angle is 60, and therefore this angle is 30. So this h and this side, which is 1 plus root 3, will help me figure out the value of h. So again, using the angles of a 30, 60, 90 triangle, the ratio of the sides are always 1, 2, and root 3. So h over 1 plus root 3 is equivalent to root 3 over 1. So h looks like root 3 plus 3. Okay, put that in here. Root 3 plus 3. All I have to do now is figure out h, the big H, and I'm done with the question. So what is big H? It's the height of the entire prism, so top to bottom. And now I need to put in a 3D diagram to sort of explain that. So here we go. So here is a 3D diagram of one sphere sitting on top of 3 spheres. And we want to figure out height, top to bottom, all the way from the top to the bottom like that. That would be this height right here. So how do we do that? We're going to break it up into 3 segments. The first segment is from here to here. The next segment is from the center of one of the bottom spheres to the very bottom. And the third is from here to the base of that triangle. You notice there's this triangle here. That is where that third distance will stop. Okay, a couple of these are very easy. From here to here, that's just the radius of the sphere, so that's just 1. From here to here, that's also the radius of the sphere, so that's 1. So now my challenge is to find this, and that is not as obvious. Well, it's not going to be that difficult. I need to label it first, so I'll just call it small h. I don't want to make any unnecessary terminology. And then remember, at the end, H, the big H, is got to be the whole top to bottom. So don't think that it's H. It's going to be H plus 2. H plus this one plus this one. Okay, so now let's talk about how do I figure out that H? Let's put, there you go, that H. Well, we are going to use Pythagoras. And Pythagoras, or Pythagorean theorem, on this triangle right here. So it's going to be this plus this and that. Those three sides will be the triangle that help us figure out H. And this being a right angle. So let's see what we can label first. This is of course H, and we don't know what it is. From here to here joins the centers of two spheres, so it's just going to be 2 times the radii. So that's just going to be 2. That's easy. Now comes the task of finding this side right here. That is challenging, but we'll be able to do it. I'll just call it X for now. Once I find X, I can easily find H using the Pythagorean theorem. So here we go. Now what I've done next to help figure out the value of X is drawn a triangle. Now that triangle that I just drew is this triangle right here. That one. I just drew it sort of flat, like a bird's eye view. And now let's talk about what is H and X. Well, H obviously is in 3D, so I'm not going to worry about that right now. I'm just going to concentrate on X right here. Well, the first thing we need to draw are these lines that are perpendicular bisectors, basically. Once you draw that, it'll be obvious what X is. X will be the distance from here to here, because this point that the H touches is the centroid of that triangle, and this is the centroid right there. So you're going from a vertice to the centroid, so that's obviously from here to here. That is X. Okay, how do I figure out X? Well, what are the dimensions here? From here to here, which is the side of that equilateral triangle, is a distance between 2 centers of the spheres. So that distance is going to be 2 times the radii. The radii is 1, so 2 times the radii is 2. So this is 1, this is 1. And therefore, since this is a right angle, this is 60. Therefore, if you chop it in half, there's this 30, and this is 60. Once again, we've got a 30, 60, 90 triangle. And therefore, X over 1 is the equivalent of 2 over root 3. So if we rationalize the denominator top and bottom by root 3, you get 2 root 3 over 3. And there you go. We are almost done. Now that we have X, I can use this triangle to figure out H using Pythagoras. So X squared plus H squared is equal to 2 squared. So we got 2 root 3 over 3 all squared plus H squared is 4. H squared would be, what's that? 4 times 3 over 9. So that's 12 over 9. So 4 minus 12 over 9. And that's going to be 36 minus 12, so 24 over 9. And therefore H is equal to, I think I can reduce this, divide top and bottom by 3, 8 over 3. So H is root 8 over root 3. Okay. Now remember, big H is H plus 2. Don't forget that. So this is going to be root 8 over root 3 plus 2. All right, we're done. Well, almost. So remember this formula. All I had to do was figure out H, or big H, and I just did. It's root 8 over root 3 plus 2. Okay, now all I have to do is crunch out those numbers. So get out your calculator and see what you get for these numbers. And when I do, I get, well, obviously 0.5 for that half. This 2 plus 2 root 3 is approximately 5.465 4, 1. Then we're going to multiply by root 3 plus 3. So that's 4.732. And then finally this guy, root 8 over root 3 plus 2. That is approximately 3.633. And when you crunch out all those numbers, you get approximately 46.97. And therefore, the volume of the prism is closest to, 46.97 is closest to 47 among the answer choices, which is E. For number, Mike has 2 containers. One container is a rectangular prism with width 2, length 4, and height 10. The other is a right cylinder with radius 1 and height 10. Both containers sit on a flat surface. Water has been poured into the 2 containers so that the height of the water in both containers is the same. If the combined volume of the water in the 2 containers is 80 centimeters cubed, then the height of the water in each container is closest to. Well, the height, they're saying, is the same. So if this is h from here to here, then this is also h from here to here. Okay. Now they're saying that the combined volume of the 2 containers is 80. So 80 is equal to the volume here and the volume there. So the volume in the first one is going to be length times width. So that's 2 times 4 times the height. The volume here is a little bit different. It's pi r squared times the height, like that. So this becomes 80 is equal to 8h plus pi r squared. Well, r is 1. That's given in the question, so this becomes 1 squared. So this now becomes 80 is equal to 8h plus pi h. Factor out the h and you get 8 plus pi is equal to 80. Isolate for h and you get 80 over 8 plus pi is equal to h. Get out your calculator. Pi is approximately 3.14, so if you add 8 to it, it becomes 11.14. And now you get out your calculator, and 80 divided by 11.14 is approximately 7.18. And therefore, the one that is closest in the answers is this guy right here, 7.2. 8 identical spheres, each of diameter 20, fit tightly into a cube of side length 40, so that each sphere just touches 3 of the faces of the cube. The radius of the largest sphere that will fit in the central space, just touching all 8 spheres, is closest to. So let's show a diagram to talk about what's going on here. Here's a diagram of this scenario where you have 8 spheres. As you can see, 1, 2, 3, 4. You can see this guy is 5, 6, 7, 8. And then they have one additional sphere in the middle right there. Now, we have to figure out the radius of that middle sphere. So we have to figure out the radius of that guy right there. So how do we do this? Well, the important thing to understand in this question is that there's a diagonal that if you draw, it will go through the middle sphere and will also go through 2 of the other spheres. And that diagonal is all the way across like that. If I do that, I know it's a little bit difficult to visualize this, but that diagonal from this corner all the way to that corner will go through this sphere. It will go through the middle sphere, which is right there, as you can see, and will go through this sphere. Okay? So the first thing I'm going to do in this question is figure out the length of that diagonal. And the length of that diagonal we can find but we have to look at a few other triangles first. The first triangle we have to look at is this one right here. That one. That one has dimensions as follows. This is 40 and this is 40, right? Because the side length of the cube is 40. So I can easily figure out this length. I'll just call it D1. Doesn't really matter what you call it, but so D1 squared is 40 squared plus 40 squared. And therefore D1 squared is equal to 3200, and if you take the square root, D1 is equal to approximately 56.568. Now I can take D1 and, considering that's a right angle, and this side 40 to figure out D2, which is the big diagonal that I'm most interested in. And therefore D2 squared is going to be D1 squared plus 40 squared. D1 squared was 3200, and then 40 squared is 1600. So D2 squared is 4800, and therefore D2 is equal to 69.28, like that. So that's the first part of the question. Very important to figure out D2. Now I have to figure out what is the radius of that little guy or middle guy, the middle sphere. So how do I do that? Now, it's going to be a little bit messy for me to draw on here. So what I'm going to do is just draw the diagonal down here. Just a line like that. Okay? Now this diagram, remember, I want you to understand that this is 3D, right? This diagram, obviously. But this diagram, I wrote it in a way that obviously it looks 2D. But I want you to just be convinced that this sphere is this one right here. Okay? This middle sphere, obviously, is the middle sphere. I think that is easy to understand. But then this sphere is here, but it's over here on the 3D diagram. It's over on the other corner. Now, this line that I just drew represents my D2. Okay? So that is very important to understand. And the reason I drew it like this is, well, first and foremost, because it'd be kind of hard to draw in 3D. But I want you to figure out that this is how we're going to interpret this question. Now, a lot of this is something that we already know, but some of it we will have to do a little bit more calculation. Now, what we know so far is that from here to here, that's just going to be the diameter of the sphere. And the diameter of the sphere, we know, is 20, right? They tell you that in the question. So this is 20 right here. And this sphere is also 20, like that. And then the small sphere in the middle, that is the sphere whose radius I'm interested in. So this is going to be 2r right there. That's 2r. Now, the tricky part is, what about this distance right here and that distance? What is that? How do we figure that out? Well, the good news is how you figure out this, that distance right there, is the exact same concept as how you figured out D2. And that is definitely very helpful. So I'll draw that again as follows. So to figure out this little distance right here, I've got to show you the following. Now picture in this box just one sphere sitting in there. Okay, I'm not going to make the diagram too messy, but just picture that. That box has to have this one sphere, and that will allow me to figure out this little distance right here. So in the very same way, we are going to draw a diagonal from there to there. Okay, and that triangle will also be necessary to figure out that diagonal. And let's start doing the calculations. Now, before we had 40 here, 40 here, 40 there, right? But what do I put in this little box here? Well, to figure that out, we have to understand, what does this point represent? That point. That point represents the center of the sphere. And that is very important, because if we know that is the center of the sphere, then we know that this distance will represent the radius of the sphere. And the radius of the sphere is 10. Okay? So that means this is 10, and then this is 10. So that, in my opinion, that's sort of the hard part of the question. So very quickly, we can figure out this guy. I'll just call that small d1. And small d1 squared will be 10 squared plus 10 squared, which is 200. So d1 will be root 200, like that. And therefore, d1 is approximately 14.14. And then we can use that to figure out this distance, which I will call d2, small d2. Small d2 squared is going to be d1 squared plus 10 squared, and therefore d1 squared is 200 plus 100, and that's 300, so therefore d2 is root 300. And that is equal to approximately 17.32. All right, so that means that we can figure out this distance right here. Remember, this was the center of the sphere. Where's the center of the sphere? It's right here. Correct? So that means this distance I just figured out was d2. So I'll just label that from there to there. And very similarly, on the other side, that will also be equivalent to d2. So that means that is d2. What about this distance right here? That's also d2. This is 2r. And then, of course, what we have remaining from here to here is just the radius, which is 10. And this is also the radius of the sphere, which is 10. So there we go. We have it all. We have the following. This whole distance is d2 plus 10 plus 2r plus 10 plus d2, and that is equal to this whole distance, which we calculated earlier as 69.28. And there we go. We have enough now to solve the question. d2 is 17.32, so put that in here. Plus 10 plus 2r plus 10 plus 17.32 is 69.28. And then at this point we just solve. So I get 2r, put everything on one side, and if you do, you get 69.28 minus 54.64, and therefore 2r is equal to 14.64, and therefore r will be equal to 7.32. That is the radius of the middle sphere. 7.32, and therefore that would be choice B for number 20. A triangular prism has a volume of 120 centimeters cubed. Two edges of the triangular faces measure 3 and 4 centimeters, as shown. The height of the prism in centimeters is. The volume of this shape is calculated as follows. The area of the base times the height of the entire shape. Now the volume of the height I can label right here h. Now the area of the base is right here. This is the base, right? That's the base, and that's also a base. Either one, same dimensions, 3 by 4. So this is 3, and that's 4, and that's 4, right? No problem. So the area of the base is just a triangle. So it's 1/2 base times height, and you can use either one, 3 for the base, and height you can use 4. And then I have to multiply all this by h. The volume they have given me is 120. So there you go. That's the equation. Solving for this, I get 240 is equal to 12h, and therefore h is equal to 240 over 12, and that means h is equal to 20. So number 21, the answer is B.